Inverse trigonometric functions. Before we look at inverse trig functions, let's do a quick review on inverse functions. If xy is a point on f, then yx is a point on its inverse. And note that f must be 1 to 1 to have an inverse. So let's remind ourselves what it means to be 1 to 1. A function is 1 to 1 if there is no horizontal line that can be drawn that intersects the graph of f in more than one point. So it has to pass this horizontal line test in order to be considered a 1-to-1 function. So if I just take a look at this graph here, which is the cosine function, so this is f of x equals cosine x, this graph definitely does not pass the horizontal line test. So if I draw a horizontal line, it's definitely going to cross more than one time. So that's something that we're going to have to fix when we think about this, these inverse trig functions. To define inverse trig functions for sine, cosine, and tangent, what we're going to need to do is restrict their domain to obtain one-to-one functions. So the regular cosine function definitely had a problem. It was not one-to-one. But if we take the portion from just 0 to pi, so looking at this blue piece here that exists from 0 to pi, so that's indicated over here on this side, this piece is definitely 1-to-1. So since it's 1-to-1, I can go ahead and take its coordinate points. So we have 0, 1 here, we have pi over 2, comma 0, and this coordinate point down here at pi negative 1. And we can go ahead and switch those coordinate points to get the graph of sine inverse, which of course is going to be a reflection over that line y equals x. So we're still talking about the same kind of inverses that we learned about previously. So this brings us to, well, what does inverse cosine then look like? So we have two different notations for inverse cosine. Y equals arc cosine of x, or also this traditional notation for inverse where it looks like to the power of negative 1, right? We don't read it like that, but it's cosine inverse of x or arc cosine of x. There's two different ways of representing inverse cosine. So this is the graph of inverse cosine. It was taking those points and switching them. So the coordinate points on here are negative 1 and then pi, and then right here this coordinate point is actually 0, pi over 2, and then this one is 1, 0. So it's taking those coordinate points that were restricted on cosine and switching the values of x and y. So this is the graph of inverse cosine. These are filled in circles, so the graph doesn't continue on forever because of that restricted domain. So for that reason, the outputs of cosine inverse, the only values that come out, the range values, in other words, extend from, well, the range is from 0 all the way up here to pi. And if we think about that on the unit circle, the values from 0 to pi are in quadrants 1 and 2. So cosine inverse outputs are only in quadrants 1 and 2. So kind of to summarize some information about arccosine here, the domain is negative 1 to 1, so it only exists from negative 1 to 1. And the range is from 0 to pi. So those y values, those outputs are from 0 to pi on the unit circle in quadrants 1 and 2. Before we evaluate inverse trig functions, I have a huge warning for you that has to do with notation. So sine inverse of x is not the same as 1 over sine x, because 1 over sine x is cosecant x, and that's not what we're talking about. Those are reciprocal functions, and we're talking about inverse functions here. So the same applies for cosine inverse and tangent inverse, that they are not 1 over cosine and 1 over tangent. Alright, in this first example, we want to find the exact value of each real number. And remember, there should be only one answer. So in this first example, y is equal to cosine inverse of 1/2. So here's what we want to be thinking about. Cosine of what angle in the interval from 0 to pi, or in quadrants 1 and 2, is 1/2. So cosine of what angle is equal to 1/2. So this is kind of what we're thinking about, is we're thinking about cosine of what angle, question mark, is equal to a half. But we're restricted to the interval between 0 and pi, to quadrants 1 and 2. So the value that we would substitute into cosine to get out 1/2 is pi over 3, specifically from this list of possibilities. So if we were thinking about the whole unit circle, then there's another place where cosine is positive, so down in quadrant 4, so there would be another solution if we were thinking about the entire unit circle. But cosine inverse outputs, the only values that can come out are in quadrants 1 and 2. So the answer here for this value of y, so this y is equal to pi over 3 only. So in this next example, I'm thinking about, so y equals arc cosine of negative square root of 3 over 2. So I'm thinking, what angle do I have to plug into cosine to get out negative 3 over radical 3 over 2? So if I go back and I look at, again, only quadrants 1 and 2, well, that forces me to be in quadrant 2 because that's where cosine is negative. And the value that we're looking for there is 5 pi over 6. So y in this case is equal to 5 pi over 6. And then finally, if we look at the last example, y equals arc cosine of negative radical 2 over 2. So once again, what angle do I plug in to cosine to get out negative square root of 2 over 2? So since I'm negative, I have to be in the second quadrant. And my option here is 3 pi over 4. So we're going to get y equals 3 pi over 4 as my answer. And then notice it said find the exact value of each real number. So remember, radians are real number values. So that's why we're using our answers here in radians. Alright, moving on to inverse sine, or the notation is arcsine, or this again, sine inverse notation. So sine inverse is actually restricted on the sine graph from negative pi over 2 to pi over 2. So just to draw a little quick sketch of the sine function, we have to restrict it again, and the restricted portion that we're going to look at is the part that extends from negative pi over 2 to pi over 2. So that little portion looks something like this. So that's the portion of y equals sine x that we're going to restrict. And then we're going to switch all those values, those coordinate points, and that's where this graph here is coming from. So this is the graph of inverse sine, and we're interested in its range so that we know what the outputs can come from, what interval they can come from. So the range here is from negative pi over 2 to pi over 2. So notice it was the restricted domain on the sine function, so now it's the range of the inverse sine function. So negative pi over 2 to pi over 2. So if I look at what that represents on the unit circle, that's going to be quadrants 1 and 4. But we have to be careful about when we think about quadrant 4, because the angles actually have to be the negative versions of the angles in quadrant 4 because of how this inverse sine function is defined. So we can't, in other words, let's say for negative pi over 4, we can't say the answer is 7 pi over 4. 7 pi over 4 is not part of the range of this graph, these y values. It has to be negative pi over 4. So that's like one little additional aspect we have to think about. So the domain of arcsine is negative 1 to 1, and the range, those outputs, come from negative pi over 2 to pi over 2. Alright, next example, find the exact value of each real number. So our answers will be in radians, and remember there should only be one answer to these. So these are functions, so there's only going to be one output. So y equals sine inverse of 1/2. What do I have to plug into sine to get out 1/2? So if I come over here, my answers can only be from these possible values on the unit circle. Since sine is positive, it has to be quadrant 1, and we know that sine of pi over 6 is equal to 1/2. So that means that the answer here is y equals pi over 6. And then y equals arcsine of negative radical 2 over 2. So again, what angle do I plug in to sine to get out negative radical 2 over 2? Well, I have to be down here in quadrant 4, and it has to be one of these angles here. So we know that reference angle has to be pi over 4, so it's got to be that negative version, negative pi over 4. And then finally, y equals sine inverse of negative 1. So the value that we would substitute into sine to get out negative 1 is negative pi over 2. So y here is equal to negative pi over 2. And lastly, we have inverse tangent or arctangent, tangent inverse. And for the graph of regular tangent, the restriction is going to be one period of the tangent graph. So one period of the tangent graph that extends from negative pi over 2 to pi over 2. So that portion of the graph looks like the x cubed graph. So it kind of has that x cubed graph shape. So we're just going to take that one piece, that's 1 to 1 there. So this is just a part of the tangent graph. And we're going to switch all those x and y values to get the inverse tangent function. So notice that the inverse tangent function has horizontal asymptotes at pi over 2 and negative pi over 2, which is where tangent had vertical asymptotes. So those x and y values, remember, switch places. So this is my graph of inverse tangent. It extends from negative pi over 2 to pi over 2 in terms of the range, but we don't include those endpoint values. So when I think about tangent inverse's outputs on the unit circle, notice that pi over 2 and negative pi over 2 are no longer options. So those values won't come out of the tangent inverse function. The other thing to note is that the arcsine and arccosine graphs are not really ones that come up in terms of future classes as much, but the inverse tangent graph is critical. So this is definitely a graph that you will be responsible for knowing, the inverse tangent function. So its general shape, which it looks like the cube root of x in general shape, but it has these horizontal asymptotes at negative pi over 2 and pi over 2. Alright, next example, give the degree measure, so slightly different instructions, of theta. But again, remember, there should only be one answer. So here, since we're being asked for our answer in degrees, we're just going to make sure that, again, it comes from these two quadrants, but we're giving the degree representation. So arctangent of 1, so what angle do I plug into tangent to get out 1? Well, that angle is pi over 4 in radians, but of course, its degree equivalent is 45 degrees. So theta is equal to 45 degrees. For the next one, theta equals tangent inverse of 0. So what angle in degrees do I have to plug into tangent to get out 0 is the question I'm being asked. So of these possible angles here, the angle is 0 or 0 degrees. So tangent of 0 degrees equals 0. So theta equals 0 degrees. And then finally, tangent inverse of negative radical 3. So since it's a negative value, I have to look to this quadrant 4. And once again, just like sine inverse, we have to use the negative angle representations, but we're going to have to convert our answer into degrees. So since we have tangent has to equal negative radical 3, so that angle is going to be negative pi over 3, which in degrees is negative 60 degrees. So theta is equal to negative 60 degrees. Now let's take a look at some properties of composite trig functions. So we're going to compose or find the composition of different trig functions. So we're going to focus specifically on when we have sine inverse of sine x and sine of sine inverse of x. So we're composing inverses. And I want us to remember this definition of inverse functions from a previous lesson, that if two functions are inverses, then f of g of x equals x, and g of f of x is equal to x. So that's what's really happening here, is we're saying sine inverse of sine of x, well, since they're inverses of each other, we get an output of x. However, since we had these restricted domains, the outputs that can come out were restricted as well. So for sine inverse, ultimately, that's the outer function here. So the outputs of sine inverse could only come from negative pi over 2 to pi over 2. And for the sine function, that's the outer function here, the sine function's range was from negative 1 to 1. So those are the only values where this property works. And then we can look at the same thing for cosine inverse of cosine x and cosine of cosine inverse of x. The only way it's going to like cancel and give us x is if we fall in the appropriate range of values for cosine inverse. So cosine inverse we just learned was quadrants 1 and 2, so 0 to pi. And since the outer function's cosine, the range of cosine is negative 1 to 1. And then tangent inverse of tangent x, well, we just learned that range was negative pi over 2 to pi over 2. And for tangent, the range of tangent is negative infinity to infinity. So the range of tangent was all real numbers. So we'll see how these properties look in terms of working on problems next. All right, find the exact value of, so here we have sine inverse of sine of pi over 5. So here we have sine inverse right next to sine. And if we were thinking about evaluating sine of pi over 5, that's not on the unit circle, so it's not something we can evaluate without a calculator. But we have this property where sine inverse and sine cancel out and give us just pi over 5, as long as we're within the range of sine inverse. So remember, sine inverse, the range is from negative pi over 2 to pi over 2. And pi over 5 falls in that interval. So we're allowed to just kind of think about these as canceling out to get pi over 5 as the answer. So let's try another one. If we have cosine inverse of cosine of negative 2 pi over 3. So what we would love to happen is we would love to say that the answer is just negative 2 pi over 3, that the cosine inverse of cosine cancels out. But the range of cosine inverse is from 0 to pi. And negative 2 pi over 3 is not in the interval from 0 to pi. So we can't just go ahead and cancel out the cosine inverse and the cosine function. So let's think about where negative 2 pi over 3 is. So since we're going clockwise, negative 2/3 of the way. So over here is going to be negative 2 pi over 3. And we wanted our answers to be in quadrants 1 and 2. So over here, the cosine function is a negative function. So remember, all students take calculus. The cosine function would be negative because tangent's the only one positive. So the value that would give us the same answer, so the reference angle is pi over 3 here. So we're looking for what's the angle that's in the correct quadrant in either 1 or 2 that will give me the same cosine value when I'm at negative 2 pi over 3. So I'm going to go ahead and put my reference angle of pi over 3 in quadrant 2 because my answer has to come from quadrant 1 and 2 only. So I'm going to put my reference angle in quadrant 2 and then go ahead and sketch my angle in standard position that gets me to that reference angle. Well, that would be positive 2 pi over 3. So positive 2 pi over 3 and negative 2 pi over 3, they give me the same cosine value. So this coordinate point, right, that corresponds to 2 pi over 3 for the cosine function is going to be, in this case, the x value is going to be negative radical 3 over 2. And then I'll look at just the x value over here at negative 2 pi over 3. It's also negative radical 3 over 2, right? And we don't need to care about the y value right now. So 2 pi over 3 and negative 2 pi over 3 give me the same x value, which is what we care about in terms of cosine. So in other words, here, instead of cosine inverse of cosine being negative 2 pi over 3, the answer in fact happens to be positive 2 pi over 3. The other way we can think about getting this particular value, because cosine of negative 2 pi over 3 can be evaluated, is, well, we can just go ahead and figure out what that is. So figure out what is cosine of negative 2 pi over 3. So I'm going to go ahead and just pull this to the side for a second. So we're going to do cosine inverse of cosine of negative 2 pi over 3, that's negative radical 3 over 2. And then cosine inverse of negative radical 3 over 2 is 2 pi over 3. So we can take it one step at a time. We can evaluate the inside first and then evaluate the outside. And that's an option on this problem because negative 2 pi over 3 is an angle on the unit circle. But notice that in the previous example, that's not an option. I can't evaluate sine of pi over 5. I have to just know and understand how this property works. So let's go ahead and try the next two, which now have sine and cosine as the outside function. So sine of sine inverse of 3 over 2. So the only way that we can cancel and get out just 3 over 2 is if we're in the range of the sine function. Well, the range of the sine function is negative 1 to 1. And 3/2 is 1.5, so that's out of the range. And in fact, the answer here is that there isn't an answer, it's no solution, because there's no angle that I can plug into sine to get out 3 over 2. So if I look at this inside part, sine inverse of 3 over 2, that's asking us, sorry to work over here on the side, but it's like sine of what gives us 3 over 2? Nothing. That's not possible. Sine only gives us values between negative 1 and 1. So if I think about the graph of sine, right, it just bounces between negative 1 and 1. So I can never get out 3/2. That's up here, right? 3/2 is above 1. So there is no solution to this particular question. But in the last one, cosine of arccosine, so I have a function and its inverse. If I think about the range of cosine, it's the same as the range of sine, negative 1 to 1, and 2/3 is in that range. So we're allowed to just cancel out and get 2/3 as an answer. So these problems really come back to knowing the domain and range for our sine and cosine functions, and therefore your sine inverse and cosine inverse functions. All right, let's go ahead and now find f inverse of x given f of x equals 2 sine x minus 1, but we're restricted from the interval from negative pi over 2 to pi over 2. And so we're going to need this restriction, of course, because 2 sine x minus 1 is definitely not a 1-to-1 function. Our sine functions just bounce up and down forever. All right, so to find an inverse, we let f of x equal y. So we're going to go ahead and say y is equal to 2 sine x minus 1. And then we switch the places of x and y. So 2 sine y minus 1. And then we go ahead and try to solve for y. So isolate the variable y. So I'm going to add 1 to both sides. So x plus 1 equals 2 sine y. And then divide both sides by 2. So I have x plus 1 over 2 is equal to sine y. And then we're going to think about that property we just learned and think about the definition of inverses. And in order to isolate y here, we're going to take sine inverse of both sides. So we're going to have sine inverse of x plus 1 over 2, and then sine inverse of sine of y. Because sine inverse and sine are going to cancel each other out, so that now I just have y equals sine inverse of x plus 1 over 2. So since y is isolated, f inverse is then sine inverse of x plus 1 over 2. So this is my inverse function, but I need to also have a restricted range on f inverse, because this sine inverse graph only exists for particular values, and we have to think about what those are going to be. So the way to go about this is we can think about 2 sine x minus 1's range. So if we know the range of f, that will tell us the domain of f inverse. So what we're going to go ahead and think about is we're going to think about what is the range of f of x, because that's going to give us the domain of f inverse of x, and that's what we need to include with our inverse function. Well, if I think about just a quick sketch of 2 sine x minus 1, so on the xy plane, 2 sine x, well, my amplitude of sine is going to be 2, so it starts at 0, and then it's going to go up to 2, and then down to -2. So to just draw one quick period of the sine function, so it's going to extend from -2 to 2, but then if I have a shift of -1 down, that's going to affect my range. So that means that I'm going to go ahead and shift everything down a unit. So this is going to end up being here at -1, so I'm going to be from here going up to this point and then going down, and this one's going to be down to -3 now. So now my range values extend from -3 to 1. So the range of f is from -3 to 1, which means that's the domain of f inverse. So we're going to go ahead and tack that on here, similarly to how it's sort of tacked on right here. So f inverse of x is sine inverse of x plus 1 over 2, comma, and I'll write it in this similar fashion. -3 is less than or equal to x is less than or equal to 1. So those are the only values on which f inverse in this case actually makes sense. So we do have to find that domain in the same way that it's provided with the inverse function. Alright, let's go ahead and do a little bit more on inverse trig functions. In this example, we want to find the exact value, so we're looking at a composition. So we have sine inverse of cosine of 3 pi over 4. So earlier we looked at when sine inverse was right next to sine, but now this is a completely different trig function, so we're going to go about this in a different way. Since this inside part here can be evaluated, we can go ahead and just find the real number that cosine 3 pi over 4 is equal to, and then evaluate the outside function. So in other words, cosine of 3 pi over 4, well, that is going to be negative the square root of 2 over 2. So in other words, this problem is asking us to evaluate sine inverse of negative the square root of 2 over 2. And then sine inverse is only in quadrants 1 and 4, and we have to use the negative angle values because we have a negative value here, so it's going to end up being negative pi over 4. So this is like the first type of example we went ahead and looked at. So that's what the problem became once we evaluated the inside. Alright, in this next example, find the exact value of cosine of sine inverse of -1/2. So again, not the same trig function next to its inverse, so we have to think about another way. And the best case scenario is if we can evaluate the inside function. So we work inside the parentheses first, and this is actually a value we can compute. So we can think about sine of what angle gets me -1/2. And it has to be from that quadrant 4, so it's going to end up being the negative pi over 6 angle. So that means this problem is really asking me to evaluate cosine of negative pi over 6. So cosine of negative pi over 6, well, the cosine function, let's remember a property, is even. So instead of dealing with cosine of negative pi over 6, that just happens to be cosine of pi over 6. So we can just absorb the negative, right? Since cosine is an even function, it just eats the negative. And so it's the same as cosine of pi over 6. And cosine of pi over 6 is the square root of 3 over 2. In this example, find the exact value of tangent of cosine inverse of -1/3. So here, we're going to work inside the parentheses, but we're going to notice quickly that we have an issue. Cosine inverse of -1/3, well, we can't evaluate that. There is no angle on the unit circle that we know of that you substitute it into cosine and get out -1/3. So what we're going to do is we're going to say this is some angle, let's call it theta. So theta is equal to cosine inverse of -1/3. Alright, well, what I can do is I can take cosine of both sides here. So cosine of theta and cosine of cosine inverse of -1/3. So that I have cosine of theta is equal to cosine next to cosine inverse is going to cancel and give me -1/3. So what I can do now is I can draw a triangle in the appropriate quadrant. So we know that this angle theta, we don't know exactly what it is, but we know that it has to be in quadrant 2. So how do we know that? Because cosine inverse can only fall in quadrants 1 and 2, and since this is negative, my angle is going to have to fall in quadrant 2. So what I'm going to do is draw a triangle in quadrant 2 with my interior angle there as theta, and I know now that cosine of theta is -1/3, which means that the adjacent side, since cosine is adjacent over hypotenuse, the adjacent side is -1 and the hypotenuse is 3. So this original problem becomes evaluate tangent of theta, because I let cosine inverse of -1/3 equal theta. So now I want tangent of theta. So if I can complete this triangle, tangent of theta would be opposite over adjacent. So if I can find this opposite side, I can find tangent theta. And I can find this opposite side because this is a right triangle, and I can use the Pythagorean theorem. So if I call this side, let's say b, then I know that the hypotenuse squared equals b squared plus -1 squared. So I get, this is 9, and if I subtract the 1, I get 8 equals b squared, or the square root of 8 is equal to b. And of course we get plus or minus out, but because this is a side length, it's going to be the positive version of 2 radical 2, which is radical 8. So now that I have all 3 side lengths, tangent of theta, well again, it's just opposite 2 square root of 2 over adjacent -1. So we never actually found the value of the angle theta, but we instead just said, well, we know that theta is cosine inverse of -1/3, which gave us the relationship that cosine of theta must equal -1/3. And then we drew a triangle in the respective quadrant, and then we're able to find the side relationship. So the actual angle theta, remember, is this angle, so it's the standard position angle theta, but we are using theta prime inside that reference triangle there, which gives us the same values on the unit circle. So my answer here, it's a little bit more simplified, is -2/2. Alright, so we do have inverse functions for cotangent, secant, and cosecant. So here the graph isn't provided. What we're really concerned with is essentially the range, right? What type of values can come out of these inverse trig functions. So for cotangent, the range is 0 to pi, so quadrants 1 and 2. For secant inverse, this looks a little complicated. It's really from 0 to pi, except pi over 2, because then secant would be undefined there. And cosecant inverse is from -pi over 2 to pi over 2, skipping over 0. So in terms of quadrants, those are listed off to the right. And then in terms of the actual angle measurements, those range values are given here. So now that we know those range values, what values can come out, we're going to try to find the exact value of secant inverse of 2. So this is equal to some angle theta. And a lot of times we don't like thinking about like secant of what gives us 2. We'd rather think about like cosine. So what we can do is start by saying, well, it's some angle theta, and so secant of theta has to be equal to 2. So if secant inverse of 2 equals theta, then secant of some theta equals 2. And now secant is 1 over cosine. So we couldn't just automatically go to like cosine inverse or 1 over cosine inverse, but we can first write secant theta equals 2 and then take the reciprocal. And now we can just flip both sides here to get cosine theta is equal to 1/2, which I'd much rather think about. Cosine of what angle gives me 1/2 instead of secant of what angle gives me 2. So I'm more familiar usually with sine, cosine, and tangent. So now that angle for theta, our answer has to be, this is what we have to think about though, we were originally trying to find secant. So our answer has to be between 0 and pi, right? Quadrants 1 and 2. So that's going to be quadrant 1, so our angle is pi over 3. So that is our solution, theta equals pi over 3. Or even going back up here, right, secant inverse of 2 equals pi over 3. So we'll go ahead and try one more here with these inverse trig functions of the other trig functions, cotangent, secant, and cosecant. This one's a cotangent inverse. So we're going to go ahead and, again, we can't, not that we can't figure it out, like cotangent of what angle gives me -1 between 0 and pi, but typically we want to somehow go back to our sine, cosine, tangents. So if cotangent inverse of -1 equals theta, then it's like cotangent of theta is equal to -1. And now cotangent is 1 over tangent, and this is like -1 over 1. Well, just flipping both sides, I can say that tangent theta is equal to -1. So now I'm looking at cotangent inverse ultimately, so my answer has to come from between 0 and pi. So whereas tangent equals to -1 in quadrants 1 and 2, well, it has to be quadrant 2, and that angle has to be 3 pi over 4. So again, I can go back up here and say that my cotangent inverse of -1 was 3 pi over 4. And finally, in this example, we want to find the exact value of cosecant of tan inverse of -2. So cosecant and tan inverse, right, are not the same trig function and inverses next to each other. And if I look to the inside here, tan inverse of -2, there's no angle that I know of that we can plug into tangent to get out -2. So we're just going to go ahead and say this is some angle, call it theta. So theta is tan inverse of -2. And again, because we can take tangent of both sides, so tangent theta, tangent of tangent inverse of -2, the tan and the tan inverse cancel, and I end up with tangent theta equals -2 over 1. So we don't, typically show this middle step here. We do just go straight to this relationship as we did on the previous 2 examples. So it's this real understanding of inverses. If theta equals tangent inverse of -2, then tangent of theta, so tangent of theta, is equal to -2. So what we're going to go ahead and do now is we're going to go ahead and draw a triangle, and that triangle is going to have to be in quadrant 4. Because we're talking about tan inverse. Tan inverse only exists in quadrants 1 and 4. So we're going to draw our triangle in 4 because tangent is negative there. So our triangle is going to be here in quadrant 4. We're going to say this is theta. And tangent is opposite over adjacent. So the opposite side has to be -2. And the adjacent side has to be +1, because +1 I go to the right, -2 I go down. So that's a very important part there. and I want cosecant of this theta. I want cosecant of this theta. Or really, again, to avoid using cosecant, I can think about this as I want 1 over sine theta. So if I need sine theta, I want opposite over hypotenuse, so I'm going to need to find this hypotenuse side. I'm going to go ahead and call it z. So Pythagorean theorem, 1 squared plus negative 2 squared is equal to z squared. So this is 5 is equal to z squared, or z is equal to plus or minus the square root of 5. So it's got to be the positive one, so z is equal to positive square root of 5. So now I get 1 over sine of theta. Sine is opposite, so negative 2 over hypotenuse, square root of 5. And this works out nicely. When I divide by this fraction, it's multiplying by the reciprocal, so I get negative square root of 5 over 2. So we actually didn't deal with one of these inverse cotangent, secant, cosecant functions. We just dealt with a regular cosecant function, but still use that idea of the reciprocal identity here. And then we had to draw a triangle. So this is definitely a technique you want to get familiar with, is drawing an appropriate triangle, and then definitely understanding this connection here between theta equals tangent inverse of negative 2, being equivalent to tangent of theta equals negative 2, and kind of going back and forth there.